Hey guys, very good morning.
Good morning, sir.
Good morning. Good morning. Are you able to see my slides?
Yes, sir.
Okay. Yeah, we discussed last class in this problem. Just to recap first a couple of minutes for refreshment. Then we go for the next few more problems. Okay. Just recap about this problem. In the last class we discussed the load on your bolt consists of axial pull of 10 kilonewton together with the transverse shear load 5 kilonewton. Find the diameter of the bolt based on the theories, all theories, maximum principal stress theory, maximum shear stress theory, and maximum principal strain theory, and maximum strain energy theory, maximum distortion energy theory. Based on that, we discussed in the last class. First, we have to find out in this problem what we have done. This first, we concentrated the direct stress. Any problem, we have to first find out the direct stress, either in component, in tensile or compressive. Okay, we have to find out the first, direct stress. Then we have to go for the next, shear force, shear stress. These are the direct stresses. And according to the once we find out this, then we know the maximum principal stress theory. Maximum principal stress sigma 1, sigma 2. Find out this sigma 1 and sigma 2. And when you are finding the sigma 1 and the sigma 2, then with help, then we are equating because the first theory is maximum principal stress theory. Hence, whatever our maximum principal stress theory, based on maximum principal theory concept, the sigma 1 is equal to our allowable limit. Permissible tensile stress, and we are equating that, then we are able to find out the diameter of this diameter of the bolt. Okay, now come to maximum shear stress theory. Similarly here, tau max is nothing but our standard test specimen. Sigma 1 divided by sigma critical divided by 2. Okay, 0.5 times of SYT. That's what we observed, and we have studied that with the help of the maximum shear stress theory concept in the hexagon diagram. Okay, region of interest. 0.5 times of SYT, and the SYT is nothing but already SYT is nothing but is the permissible tensile stress, not directly SYT. Okay, here SYT is permissible tensile stress is directly given. Okay, yeah, please 1 minute, just a minute. So here the permissible tensile stress is directly given. Suppose if it is not given, it might have been given SYT yield strength, or else we can take it from the data book that must be divided by the factor of safety. This is now factor of safety already divided. Hence, this is 100 megapascal. We are directly taking permissible tensile stress into 0.5 here. Okay, as per the shear stress theory concept. Then the shear stress theory concept, the left hand side, we are considering finding the tau max in terms of diameter square is equal to 50 megapascals permissible shear stress. Then we are finding the diameter of the bolt. And similarly, we are using the maximum principal strain theory. This is the maximum principal strain theory concept. Where it is? This one. I mean, whatever we discussed, the same procedure here, the finding sigma 1, sigma 2. But see here that the principal stress theory, maximum principal strain theory concept is sigma 1 by E minus sigma 2 divided by E into mu, because strain is playing, hence must be the Poisson ratio. Then right side is as it is. I mean, sigma right side is now whatever the permissible stress 100 megapascal. Okay. Then we are finding the diameter from this maximum principal strain theory. Okay. Then maximum shear strain theory. Here maximum shear strain theory. This is this same way we are finding the principal stresses. Finally, we are applying the maximum maximum strain energy theory. Maximum strain energy theory. See here, this is the equation. The left hand side is sigma 1 squared plus sigma 2 squared minus 2 sigma 1 into sigma 2 divided by m is equal to right hand side is the standard specimen and our permissible limit stress. Okay. This is strain energy theory. Strain energy. It's not a strain theory. Okay. So now we can find out the diameter of the bolt. I mean, based on the maximum strain energy theory concept. Then finally, we are coming to the we discussed that in the last class, distortion energy theory. Based on distortion energy theory, this is equation sigma 1 squared plus sigma 2 squared minus 2 sigma 1 sigma 2 is equal to critical stress squared. Its critical stress is nothing but now permissible limit. That's what we are putting equal. Okay. Now, from all this theory, finally we found out that, I mean, based on this theory, we have found that the diameter of the shaft is 13.4 mm. Then finally, we can come to the conclusion, I mean, 13.4 mm, I mean, approximately 14 mm diameter of the bolt, it will be suitable for this load and stress. Okay. So that's what we discussed. Come to the next problem. A mild steel bracket, as shown in figure, to a 2-point this figure, is subjected to a full of 6,000 Newton. Because here the 6,000 Newton, it's acting 45-degree angle of orientation on the top of the bracket. Okay, to the horizontal axis. Now the bracket has a rectangular cross section. Bracket has a rectangular cross section, rectangular section. The bracket has a rectangular, the bracket has a rectangular section. The depth is given twice the width. I mean, the depth is given B by T. B by T is equal to 2, twice the width. Now, our aim is to find the cross-sectional dimension. They didn't give the dimension of the bracket, I mean, that is a rectangular section. Now, our aim is to find out what is the dimension, but they have given the permissible stress of the material. I mean, they have given directly 60 megapascal. Then, I mean, this problem is a little different, whatever we discussed. This problem is totally different to whatever we discussed in the earlier problems. See here, first find out the area of the sectional area of the bracket here. I mean, we don't know dimensions, but they have given the depth by width ratio. I mean, based on that, we can find out that the area of the cross section in terms of T, then it will be area is equal to 2T squared, and the section modulus is nothing but B d cube by 12. You know already, right? B d cube by 12 whole divided by d by 2. That is section modulus. B dq by 12 is nothing but amount of, I think, I, right? Amount of inertia. Amount of inertia divided by y. Y is nothing but again 2t by 2. Then it will become section modulus. You apply that concept, you are going to get 4tq divided by 6. Now here this is the load is acting 45-degree angle of orientation on the top surface of the top side of the bracket. Now this component can be resolved into two components. This resultant component, they have given the resultant component 6000 Newton, that can be resolved into two components. One is vertical components, other one is horizontal component. Now, when the load is acting angle of orientation, obviously it will be a two components should be there. So be clear. Keep in mind, because this kind of problems you may expect any exam. Okay. So see here, this is a 6000 Newton. Then we would like to find out the horizontal force and vertical force with respect to angle 45 degree. Then find out this horizontal force on the bracket is 6000 into cos 45. Then 4242 Newton horizontal force. Here the 45-degree angle, it's obviously in vertical directions also, that the forces will be same. Okay, first we finish this one by one. Now the bending moment. Here horizontal force is given, vertical distance is given. Because the force is acting offset from the axis of the bracket, where the bracket is fixed with the support. Okay, then absolutely it will be a vertical bending moment and horizontal bending moment. When we are calculating the horizontal bending moment, we are considering the horizontal force into vertical displacement. Okay. When we are considering the vertical bending moment, we are considering the vertical force into horizontal distance. Here horizontal force into vertical distance, pH into 75. Then it will give us the horizontal bending moment. Okay, bending moment due to horizontal component of the load. Sorry, bending moment with respect to horizontal component of the load, and vertical bending moment with respect to vertical component of the load. Then vertical load is nothing but 6000 into cos sine 45. Now you can see here. Okay, see here, a little considerations will show that bending moment due to the horizontal component and of the load induced in the tensile stress and the upper surface of the bracket, and the compressive stress on the lower surface of the bracket. The statement you can understand while seeing the figure itself, you can understand that. See here, when the vertical load is acting, which layer is compressive, which surface is going to be a compressive tensile, you must know, right? Because see here, this layer, top layer and bottom layer. In the top layer may be tensile, bottom layer may be a compressive. So based on that, you can understand this is a basic theory. So now we can find out the maximum bending stress on the upper surface of the horizontal component. See here, we know already horizontal bending moment. The bending moment with respect to horizontal load. Then we can find out the tensile stress. Because while in generally I told the earlier statement, now I tell you that while considering based on this figure that the top surface is going to be a tensile, while while considering the pH, load pH is acting on the bracket. Okay, that's what we are considering here, tensile. Okay, the vertical load of the bending moment. Now the bending moment going to, now we are calculating with respect to vertical load of the vertical component of the load. The bending moment is like load is 4 to 4 Newton. Due to that stress, due to the vertical components, vertical component. This is a direct stress. Direct stress is, what is the direct stress? PV by A. PV by A, we know that A is nothing but 2T square. This is a direct stress tensile. Bending moment due to the vertical load is, 5.51 e power 5 Newton millimeter. Now we would like to find out the bending stress with respect to vertical bending moment, mv by z. Then vertical bending moment, this is also tensile. The upper surface going to be in tensile because the load is acting downward, hence the top surface of the bracket is going to be tensile. Top surface of the bracket going to be tensile and bottom is going to be compressive. Then vertical bending moment, based on the vertical bending moment, we can find out the bending stress on the bending stress on the top surface is tensile. Then we are always finding all the bending moment, stress with respect to horizontal, with respect to bending moment. While considering horizontal load. This is bending stress with respect to horizontal load, but it's not. We are not considering horizontal load. Horizontal load, the bending moment has been found with respect to horizontal load. That's what we are putting sigma BH. The sigma BH is nothing but 477,225 divided by R cube in terms of T cube. Sorry, T cube. We have found. Similarly, vertical bending moment, we found it first. Then, with the help of the vertical bending, we are finding the stress. Okay. Now, the total tensile stress, summation of these two stresses, both are in tensile on the top surface, and the direct tensile are there. Here, direct tensile also there, and both with respect to two bending moments, vertical bending moment, horizontal bending moment, there are two tensile stress components. Then three tensile stress components. The first one is direct tensile. Where is the direct tensile? Yeah, this is with respect to horizontal bending moment. Sorry, this is the first component with respect to horizontal bending moment. Second one is with respect to direct tensile stress. Third one is with respect to, vertical bending moment. Bending stress, the tensile stress. Okay. Now submit all the things, you are going to get like this equation. Now we know that our standard permissible limit is 60 megapascal. Then equate this equation with the 60 megapascal. We are able to find out our dimension T of the thickness of the bracket.
Hello, sir. Excuse me.
Yes. Tell me,
sir, why is it that we are not taking direct stress with respect to horizontal components, sir?
1 minute, I come here. Horizontal component, right?
Yes, sir. Direct stress of horizontal component.
See, but horizontal component, we are taking bending moment, right? The horizontal component is not acting in the axis of the bracket, right? But this is the vertical load is acting on the bracket axis. It's vertical axis. No, this is, see here. 1 minute. I come to this your question. Yeah, PV by A. This is a direct. Yeah, you got good question. Yeah, this is very good question. I didn't think of that. Yeah, you are correct. Usually we have to consider sigma V is equal to PV by A. This is the with respect to vertical component of the bracket. But I hope that now I think about that. Whatever you asked the question. Now see here. When we apply this, it should be considered because this is a direct.
Sir, I think with vertical component we only get bending moments, sir. No direct stress.
No. Vertical load component also bending moment. See, vertical force into horizontal distance. 130 mm, right? That we can't avoid. There are bending moments with respect to horizontal component and another bending moment with respect to vertical component. We can't avoid that. But here your question is valid question. I verify it later, but why they consider only vertical bending moment, I will think of that. I will tell you later. Okay. Sure, I will point out in the next class. Okay. Here PV by A only they considered vertical load. Vertical load.
Sir, what I am saying is that the direct stress will not be anything for vertical components, sir.
No. The horizontal load is there. That yeah, 1 minute I come to that conclusion. That see, okay, now I come to the conclusion. I clearly tell you that. See how I got it. See. Now our region of interest here only. Okay. Then this portion, when it will be stressed, when the load is acting here, then this portion going to be stressed. But hence we are considering vertical bending moment, vertical load for direct stress. Suppose our region of interest here, then during that time we can consider horizontal load for direct stress. Horizontal load for direct stress. But in this case, whatever you have been told, that is also valid points, that horizontal load may not be accommodated in this region of interest because the horizontal load is offsetted from the axis of the bracket, main axis of the bracket. Are you clear now? But if you take this portion, then during that time we have to consider both pH and PV. Okay, during that time pH is tensile, PV is incompressive. If you are considering this region of interest, they have clearly mentioned there. Find the cross section area of the bracket based on this region of interest. Are you clear now?
Yeah, thank you, sir.
Yeah. Still, if you have any doubt, please we will discuss in the next class also. No problem. This is very clear now. So now finally we come to the diameter. Thickness of the bracket is 28.9 mm, 28.4 mm. Then B is equal to 2T. They already given. Depth of the bracket is now 56.8 mm. Now around 57 mm. Now they come to the last. Next problem. A clamp as shown in figure here. See here. Yeah, here. This is a clamp. This is a different problem. Very important problem. Because I tell you one thing, I have gone through the books, many books. Most of them they are playing with this problem only. They changed the values only. They changed either stress value or dimension or loading value. The load value, P value, they are changing. Most of the books, this is a common problems. But if only you have to understand the concept, how to apply. Now we know how to apply how we are applying the earlier strength of material concept, bending moment, horizontal bending moment concept, vertical bending moment concept, how we are applying. That is important. Okay. Now, see the clamp shown in figure carries the load 25 kilonewton. The cross section of the clamp is, this is a cross section of the clamp. We would like to find out this, dimensions of the clamp here. This cross section. Okay. Rectangular having the cross section of the clamp XX having the rectangular, having the width is equal to twice the thickness. The width is given equal to twice the thickness. W is equal to 2T. Assuming that the clamp is made of steel, they have given directly allowable stress 100 megapascal. Find its dimensions. Also determine the stresses at the section XX and ZZ. Now, they are not only asking these dimensions. First our target is to find out this dimension. Then our next target is to find out the stress components acting in the YY section as well as ZZ section. Our target is to find out, first target we have to find out the dimension of the clamp, and so the second, once we find it out, then we are going to find out this stress of this sectional area. In this section area, what is the stress component? I mean, in this section area, what is the stress component? Now, I come to your question, further clarification, earlier question. Now, see here, I mean, in the whatever now I explained there, that the next question, no? In the next question, you are going to get a different stress value in this component. In this YY section and ZZ section, we are going to calculate. Hence, if we are considering this region, then the two forces are going to be considered because this is a direct compressive and direct tensile. But when we consider this region, it's totally offset from this, I mean, pH value. Hence, we are considering only bending moment with respect to horizontal load. But even still, I have some doubt. Even you may consider, I can strongly suggest, you may consider this pH also for safe design. That is my, I mean, once you ask the question, then I have understood that it should be considered also. But anyway, I will verify it other books also. But this is the one appropriate answer if we considering.
Sir, we should consider it, sir.
What, pa?
Sir, we should consider it.
Yeah, that's what. That's what. Based on my observation, we should consider. But in this cross section, if we consider this cross section, obviously going to be considered both load for finding the thickness of the bracket with respect to compressive, direct tensile. Okay. Yeah, even if you consider, it's right only. You can demand that I'm considering horizontal load. Obviously, this load, it will be impact on the axis of the beam. There's a pH also. You can consider. Okay. Are you clear? Who asked this question? Kindly let me know, please. Hello?
Sir, Abhilash Reddy Gadam.
Okay, thank you. Okay, now come to this question. See, they are given load is 25 kilonewton and maximum stress is 100 megapascal. This is a permissible stress. Okay, and Newton per mm squared. It's not Newton per mm. Okay, I mean the dimensions. First, we are targeting is finding the dimensions of the section XX, the thickness of the section. Okay, we would like to find out here, and width is given two times of the thickness. Now, see here. I mean, when the load is acting in the C clamp outward direction, the load is acting outward direction. The load is applied at the inside of the clamp, but the load is acting outward direction of the clamp. Hence, the section XX section, the inner XX section going to be subjected to tensile stress. Okay, tensile stress. Direct tensile stress is nothing but P by A. Now P is nothing but 25 kilonewton. A is given, I mean, in terms of T, 2T. Width is 2T, breadth is 2T, width is 2T, and thickness is 2T. Then we are able to find out the area of the area of the cross section 2T squared. Then this is a direct stress in terms of T squared. Okay.
Sir, isn't this question similar to the previous one? Like we have a cross section and force is applied at the offset from it, and we are considering the direct tensile stress over it.
Yes, yeah. That's what I once I seen that. You are correct. What you are trying to say finally, we have to consider that horizontal load. Based on horizontal load, we have to consider the tensile stress, right? Are you trying to say that?
Yes.
Yes, I agree. We have to consider. Okay. And now see here the bending moment. Now here vertical load and horizontal distance. When we have vertical load, horizontal distance 140 mm, then we are finding the bending moment. I mean 225 into 10 power 3 into 140 mm. This is a bending moment with respect to vertical load in the section XX. How much bending moment? Then here this is the section modulus, you know, right? In terms of T BDQ by 12 and Z. Then we can find out the bending stress in this along this section XX. This is a tensile. The direct stress also in tensile, right? Then finally I mean, finally, summation, superimposing of these two stresses. I mean, sigma A direct, sigma naught here direct, and sigma B is a bending tensile due to bending moment. Then sum it. Then finally equating with respect to our permissible tensile, permissible stress 100 megapascal. We are able to find out the thickness of the clamp. Thickness of the clamp is finally we are getting 38.5 mm. Width of the clamp is we are getting 77 mm. Okay, now section, stresses at the section YY. The first portion of the problem we completed. Once we know that, then only we are able to find out this section, how much force, how much stresses are acting. Now the section, now the cross section area is, what is the area of the cross section? This is a 45 degree. Then area of the cross section, we would like to find out the cross section area along the YY section. Okay, hence we are using that area into 1 by b into b by sine cos 45, b by cos 45. Then this area we would like to find out cross section area, not in this horizontal area or vertical area. Cross section area, it will be more than the horizontal cross section. Okay, hence b into b by cos 45. Okay, and then we are able to find out the area of this cross section. Here the B is already given. Already we have found it 75 mm, 77 mm. 1 by cos 45 into T. Okay, then 77 into 1.414, then 5 into 38.5. Then finally we are getting the area of this cross sectional area is 4192 mm square. Similarly, the component of load load perpendicular to the section. See here also the load is going to be at two components. In this cross section, we would like to find out what is the load in this section. In this section, we know that the load, P is a vertical load. This P vertical load into cos 45, then we are getting 17.675 kilonewton in the component load perpendicular to the section. The component load perpendicular to the section. Okay, then uniform tensile stress over the section. The tensile stress over the section is nothing but a direct stress. Direct stress. Because this is a direct stress also. Here also direct stress, right? That's what we are finding, this a component perpendicular to the section. Perpendicular to the section. Now, once we find out the perpendicular to the section, we already know the area, then we can find out the stress in the component. It looks like a direct stress. Then the direct stress is a 4.2 megapascal. The component load parallel to the section, P sin 45, because this P going to be resolved into two components in this section. One is P cos 45, one is P sin 45 in this cross section. Hence, the component load parallel to the section going to be a P into sin 45. The P is already given here. Okay, this is axis is parallel, right? Hence, we are using for cos 45 and sin 45 for finding the perpendicular component of the force and parallel component of the force. P sin 45. Then this also same load, same magnitude. This component of the load produce the uniform shear over the sections. Now tau into shear area. Here, the sin 45, cos 45 both are same value. Hence the load is similar. The load is similar. Then the area, the shear stress also similar, 4.2 megapascal. Suppose cos 30 or sin 30, then that value going to be different. But here the both value, the sin 45 or cos 45, both are same value. Hence we are getting both are in same stress, same value. Direct tensile stress and direct shear stress both are in same value. Okay. This is nothing but this region. What we studied, this oblique plane in the principal stress. This is our looks like oblique plane. Sigma and tau direct in this. Okay. Now I come to this. Okay. Now we know the section modulus, right? Section modulus is b d cube by 2, b d cube by 12, and the d cube is nothing but we are considering b d cube. The b is nothing but we are considering b into sin 45 because the cross section. This is just I put a reminder here, right? This cross section is always this region always greater than B. Sorry. Hence, B by cos 45, then B secant 45 squared divided by 6. We have to consider this dimension while calculating the section modulus or finding the finding the bending stress or bending moment in this region of interest. Our intention is what is the stress is going to be acting in this region. That's what we are considering. Now bending moment. In this bending moment, we know, right? What is the bending moment? This is the vertical load, horizontal distance. Vertical load here, horizontal distance is 140 mm. 140 mm, then 140 into 25 kilonewton, then I can find out the vertical, bending moment with respect to vertical load. Then find out this bending stress. In this region, this is the what type of stress? Bending is the tensile or compressive. Now, the bending moment, whatever we are finding the stress of the component is tensile or compressive. Please tell that. In this region now, tensile or compressive. With respect to bending moment, the stress generated, the stress created in this region is tensile or compressive. Hello?
Sir, inner one will be in tensile and outer one will be compressive.
Yeah, but overall, we are taking as this region that inner layer. The inner layer is small radius as compared to outer radius, right? And mostly this region going to be in this case, it will be a compressive, right? It will be a compressive. We are considering compressive. We are not considering here inner layer or outer layer like that. It will be a complicated problem. Only we are, average we are considering as a compressive because the load is acting upward direction, hence we are considering as a compressive. You are correct. But if we want to go this finding exact this curved region, this fillet region, the stress component, we have to play with other complicated equations. Okay, anyway, that is we are not discussing that, but we are considering as a bending. Due to bending, maximum tensile source inner and the maximum compressive stress, maximum inner is tensile. You are correct. And the maximum compressive stress on the outer region of the product. But the maximum tensile at the inner, we can consider already we have found it, right? Already we have found it. What we have found? 4.2. Oh, sorry, you are correct. Sigma tensile, it's a bending with respect to bending stress. With respect to this, we are considering the inner region, inner radius. Okay. But I am wrong. I sorry for that. I little confused because yesterday I tried to give one more problem in this. Chain hook. In the chain hook is totally different. So that's what I told you that wrong information. Sorry for that. Avoid that information, please. Okay. In the chain hook, it will be acting different orientation. It's now you have to find out the centroidal axis and how much distance the load is acting, how the centroid axis shifted from the offsetted. Then we have to go for complicated equations. It's not UG level. Okay, that's the based on that I suddenly told that information. Sorry for that. Okay. Yeah. But finally, I didn't prefer that sum to you. Okay. Now come to this, the maximum tensile stress at the inner surface. We know the bending stress now. Inner surface is going to be tensile. Then direct stress is going to be 4.2 megapascal here. 4.2 megapascal direct stress. Okay. Here. And this is shear stress. Okay. Now we can find it out the maximum tensile stress at the inner surface. Similarly, we can find out the maximum compressive stress at the outer surface. Compressive stress at the outer surface is nothing but sigma b minus sigma naught. Sigma b minus sigma naught, but sigma b minus sigma naught, this is a compressive stress. Okay. Now we know we have to find out the principal stress. There are two stress components. This is looks like sigma x and sigma y, right? Yes, this is with respect to this, we are going to find out this stress component with respect to this component and the shear stress component. Shear stress component we know. Then with respect to this sigma c and shear stress component, we are able to find out the minimum stress, minimum principal stress. Okay, this and this. This is these two components, we are able to find out the maximum principal stress. These two stress component, we are able to find out this. I mean, this is sigma max. This will give sigma mean. Okay. Then substitute this our maximum principal stress theory concept. Maximum principal stress. Okay. This is sigma 1 will give you 50.5 megapascal. And substitute this. I mean, now find out the maximum principal stress and with respect to compressive. Yeah, sorry. This is with respect to tensile. This is with respect to, this is not tensile, with respect to compressive. This is inner region. This is outer region. That's all. Okay. Then you can find out compressive stress with respect to this and the maximum shear. Once we know sigma 1, this is looks like sigma 1 and sigma 2. Okay. Sorry, I'm confusing. Sorry, boss. No. I mean, this is directly given. This also similar to you have to find out. Okay. Yeah. Now sigma c is given. I mean, sorry. Here this is maximum shear stress. We are considering maximum during maximum shear stress. We are considering this only 50 megapascal, and the tau is here. We are considering 50 megapascal, 50.2 megapascal, and tau is 4.2 megapascal. These two components we are considering. Okay. For finding the maximum shear stress. Suppose if you want to find out the here we know directly 50.2 megapascal one stress component, that is normal stress component, and 4.2 is our shear stress component. Then these two we are considering for finding the maximum shear stress. But here the magnitude of the other component sigma c we know 42 megapascal approximately. Suppose sigma c is going to be a 60 megapascal, then we have to consider, I mean, this 60 megapascal for finding the maximum shear stress. Okay. Yeah. Okay. I mean, one more time I clarify this. Here also little distraction. I mean, when we are considering, when we would like to find out the stress component along the YY axis, YY cross section. In the YY cross section, this point going to be a tensile. This point, outer point going to be a compressive. Outer point going to be a compressive. Inner radius going to be a tensile. Then we would like to find out each point the stress component. That's what our intention here. I mean, once we find out each point the stress component, then we can find out the maximum principal stress, either compressive side or tensile side. Okay, that's what. First, we are finding this component based on the compressive behavior, while the bending moment with respect to bending moment, right? Then based on the tensile behavior, we are finding this. I mean, here, this one. I mean, tensile at the inner surface. Tensile at the inner surface, we are finding the 50.2 megapascal. This is a direct, 4.2 is direct stress, and 46 is with respect to, I mean, bending moment. Okay, the stress is acting here. Then we have found this, the maximum tensile stress at the inner surface. And the second case, in the outer surface, maximum compressive stress with respect to bending moment, here compressive load and compressive stress created, and actually here that the direct stress is going to be a tensile, then it should be a minus sign. Either any one of the things, it should be a negative sign. Hence, we are finding the compressive at the outer region. Now, once we found the outer region and the inner region, there are two stress components. Whatever I slightly here also I confused, please avoid that. Okay, this is not a sigma max. We would like to find out the stress at this inner region with respect to principal stress theory, not maximum principal stress, with respect to our principal stress what we studied, no? Then we are finding this region because here the component tau and sigma is there. Here the component tau and sigma is there. Then I am going to substitute these values tau and sigma in the our maximum principal stress equation. Then finding here what is the maximum stress is acting. Then I know already here this is the load sigma value. I know around this is the tensile region. I mean we know that 50 or 50.2 megapascal, and the shear stress is a common 4.2 megapascal. Then we are able to find out what is the maximum stress in this region when you substitute in our maximum principal stress equation. Then in both the point we are able to find out the stress component. Finally we came to that. I mean this is the maximum stress acting in the YY region, especially inner and outer corner of the clamp. Outer of the corner of the clamp is, now we came to know that this is the, this is the at the outer corner 40 megapascal. I first remove some of the things, otherwise it will be confusing. Okay, tau is common, but sigma is here compressive, here tensile. Okay, now find out, then this is a tau and sigma coordinates now. Then substitute in the maximum principal stress equation. We are finding the stress at the outer corner and inner corner. This is the, here also I remove it. This is the, this is the inner corner maximum stress and inner corner, and outer corner these two components sigma and tau plug into this same maximum principal stress equation. Then we are getting this, but in compressive nature. Okay, compressive nature. Finally, maximum shear stress. Here also we should find out, with respect to these two components, but here directly we are considering which one is maximum stress. Which one is maximum stress? This is a maximum stress. Hence, I am considering this component to find out the maximum shear stress. If I consider this component, this is not a maximum shear stress presented in this, in this region of interest. But even though here, what is the considerable stress here? The design going to be considered 50.5 megapascal. We are not considering this. Okay. Now come to this section ZZ. Sorry, section ZZ here. Yeah, this is section ZZ. Finally, we come to the section ZZ. The section ZZ is 40 mm offsetted, 40 mm away from the force acting on the clamp. This is our region of interest now, especially this region. 40 mm from the load acting, where the load is acting 40 mm away from the ZZ section. Now, the ZZ section is, it's not a, angular orientation. The cross section is, perpendicular. Then it can very easy, you can find out the stress component in this region. What is the bending moment? Here, the bending moment, vertical load in the horizontal distance, only one component, because here already given this region earlier, what we discussed, the inclined region. Hence, we considered both vertical component and horizontal component of P into cos 45, P into sin 45. Then we came to each point, what is the stress component, we have found it. Now, we come to this ZZ region, vertical region. Then the bending moment with respect to vertical load into horizontal distance, then 225 kilonewton into 40. This is our bending moment. Now bending moment. Now what is the stress acting here? The stress is M by Z. Very simple form. Very simple. This ZZ region, finding the bending stress. Then direct formula M by Z. You can find out what is the bending moment in this section ZZ. And here, I mean, the bending stress in tensile in the inner edge and compressive in the outer edge, the magnitude of the both the stresses are in 26.3 megapascal. Okay, because 26.3 megapascal, anyway, based on bending stress. The neutral axis, there is only transverse shear. The shear stress at the inner and outer edges will be 0. I mean, we already discussed. Anyway, I have one slide. I will show you that now. I mean, usually the transverse shear, the shear stress will be inner and outer edges will be 0 and maximum at the mid layer, right? I mean, that's what we discussed. No? This is inner layer and outer layer 0 during shear stress when the torsion is acting. But we discussed the shearing stresses. This is in the middle layer. This is outer layers. But in bending stress, maximum at the middle, and this is the middle layer. It's a neutral layer, 0. And maximum, this is a tensile. This is a compressive. This is in bending stress, sigma B. This is in tau, right? Shearing stresses. Maximum at the, I mean, middle, and both edges are 0. Now, how we are finding the, we are using this tau max is equal to 1 by to 1.5 averages here. I show you one, PDF form. I will share you that PDF also to you later. Yeah. So come to here. See here. This is the, I collected from the strength of material. So this you might have been studied. This is a shearing stresses. Shearing stresses in the uniform cross section of the bar. Shearing is a uniform cross section of the bar. I mean, here the tau is going to be proved, derived that, I mean, shearing force S into A y bar, S into A y bar divided by IB, moment of inertia into width of the beam, width of the bar. Now, see here, I mean, variation of shear stress in beam cross section. I hope that you might have been studied. Anyway, I will share you this later. I mean, the shadowed area, this shadowed area, now we are considering for the finding the maximum shearing stress in the rectangular cross section. I mean, the rectangular cross section, see, this is very simple derivation. You go through that, you can get it. See here, this is a rectangular cross section. I consider this is the neutral axis. I mean, this is the neutral axis, y distance, the small elemental area, section area I'm considering from the neutral axis at y distance. But y bar is with respect to the center portion of the centroid portion of the, center to the neutral axis distance. I mean, which section area I considered my evaluation, that center to centroid neutral axis distance is y bar I'm considering. Now that maximum shear stress is acting at the middle of the bar, rectangular bar, and both outer layers are going to be 0. Finally, if you go through this derivation, very simple derivation, please go through that, you can understand. Finally, they came to know that tau max is equal to 3 by 2 tau mean. Similarly, you see that solid circular section, I am considering this neutral axis. I mean, which section I am considering the sectional view, that is, apart from the y bar distance, apart from the neutral axis. I mean, the small section, the small, the delta y section is, y distance, offsetted distance from the neutral axis. Just you apply the concept, you can basics, you can apply the basic, you can derive this equation easily. But anyway, this is already you might have been studied. Here, what is the tau max here? If I am considering circular cross section, the tau max going to be 4 by 3 into S by pi r square. If I am considering tau max in the circular cross section of the beam, circular cross section of the bar. But I hope that you might have been understood now. I come to the problem now. See here, what is this problem? Here our problem is rectangular cross section, because T is 38.5 mm and B is the 77 mm rectangular cross section. Hence, I used that concept to find out the tau max. So, finally I came to the tau max is equal to 1 by 5 times. That's what we just now we have seen, 3 by 2 tau average. Now 3 by 2 is 1.5 into tau average. then P by PT. P by BT is nothing but, I mean, whatever we discussed, this is nothing but 4.2. I mean, earlier we discussed not tau. P by BT, 1.5 into P by BT. Then we are finding the tau max in this region, in the section ZZ region. Okay, but here, whatever we discuss here, this tau max is different because this is looks like oblique angle, oblique plane, right? This is whatever we discussed the beginning class, this plane. Hence, we are applying the principal stress theory here, principal stress equation. Here we are directly considering the shear stress equations, whatever I shown, what I have shown in the PDF format, you go through that. This is for rectangular section. I have attached this rectangular section and square and circular cross section. Circle, if the clamp is circular cross section, the tau is different. Tau max is going to be different. Okay, what is tau max in circular cross section? Tau max in circular cross section is tau max is 4 by 3 into pi r squared. This is the load. S is load. Now our P 25 kilonewton. This is 4 by pi r squared. So in tau max for circular cross section, I attached a few cross sections. Please go through that. So if we have any doubt already, what is time? Already 9. My God, I thought to finish today. Okay, anyway, few more problems. Very simple problem. We discuss in the next class. And sure, we are going to start next class. We are going to start our next chapter. I mean, that is next chapter. Going to start and it's a dynamic against the fluctuating loading. Now, whatever we discussed today, I mean, static loading. Next class, we are going to start design against design of component based on fluctuating loads. The fluctuating loads, we are going to concentrate on the, I mean, discontinuities. It will be presented in the component. Whatever we discuss, any component, did we discuss anything presented in the holes or keyways? No, because these are all plain geometries without any discontinuities we discuss as of now, and static loading. But in the later chapter, we are going to discuss in the next class fluctuating loading. I mean, design the components based on fluctuating loading. It will be presented in the discontinuities. Then what is use of discontinuity? Those things we will discuss in the next class. I mean, these are the problems, simple problems. I will take maximum 30 minutes. Sure, within 30 minutes, I will be able to complete. Because we covered most of the things. Then I gone through our syllabus and whatever we discussed in the beginning. Then these are the problems missing. I mean, some load, offset load is acting on the bar, missing the problem. And simply supported beam problem missing. Okay, simply supported beam concept problem is missing. And one more thing, the tangential load acting in the crankshaft and determine the maximum principal stress. Based on that, how to define the dimensions of the crankshaft, that problem also missing. Okay, I mean, simply supported beam concept problems are missing, and offset load problems are missing. Then those problem, and one more problem, I mean, the two simply supported problem, beam problem. I mean, not simply supported beam problem, the simply supported beam concept we are going to use to define or design our component design. For example, diameter of the shaft. So those kind of problem missing. So we will discuss in the next class. And the tangential load kind of problem also missing. We will discuss in the next class. Okay. Please, if you have any doubt, please go ahead. I'm ready to clarify. I come to chart box. Yeah, Sakil, I was there in the presentation mode. I unable to see your question. Yeah, please tell me, Sakil. Sakil, are you there?
Sir, like he was talking about the question we were discussing, right? Horizontal component should be included in direct shear or not.
Yes.
So you explained that it should not be included. So he was telling about service again how it is not included. But yeah, we are not still concluded about it.
Now, are you okay, Jace?
Yes, sir. I am okay, sir.
Okay, you can consider. Okay, which you can consider. We have to consider, no doubt at all. And I mean, there are, wow, somewhere I slightly I mean confused. That thing also corrected. Okay, please. Some of the unnecessary information avoid it from this discussion. Okay, any doubt, please? Okay, next meeting. In the next class, we are going to start fluctuating load. First 25 to 30 minutes, maximum 25 to 30 minutes, these problems, and I mean, then we are going to start our third chapter. Okay. Thank you, Karthik. Thank you, Sakil. Please, if you have any doubt, please go ahead. Otherwise, shall I close the meeting? Pawan, are you there in the meeting?
Yes, sir. I'm there.
Okay. Are you
Yes, sir.
clear? If you have any doubts, please, you have a time. You are going to have class at 10. Na?
Yes, sir.
If you have any doubt, please. I am also going to have class.
No doubts, sir.
Okay, guys.
Thank you, sir.